Okay, Assalamu alaikum, welcome back to EE340. So in the previous lecture we talked about pointing vector, and in the lecture before that we talked about wave propagation in unbounded media. So in this lecture we want to consider the wave propagation in some sort of like semi-bounded media. So the wave will go from one medium, let me call it medium 1, to another medium 2. And we want to study what happens at the interface and what's the field, given the field at medium 1, what will be the electric field and magnetic field at medium 2, and what kind of, in terms of magnitude, phase, and direction of propagation. So let's get started. Instead of solving this equation, let's derive this equation. So let's assume that we have this current situation. So we have, this is the x-axis, this one is the z-axis, this is the z-axis, this one is the x-axis, and the y-axis is pointing out of the page. The electric field that we have, or before that, the wave is propagating along the positive z direction, so this is AK. Again, this one is 1. And in this half space, we have medium 2. That medium is that medium has conductivity sigma 2, permittivity epsilon 2, permeability mu 2. Similarly, in this region we have medium 1, and medium 1 is characterized by sigma 1, mu 1, epsilon 1, mu 1. So let's assume that the electric field that we have can be written in the following form. So we assume that the electric field is propagating, the electric field has an x component, and this is the incident field, and it's function of z. This is the magnitude of that, and the medium is actually general medium, so let me call this one gamma 1z, and the electric field has only an x component. So the magnetic field should have a z component. Should have a y component, and we can assume that the magnetic field is given by this equation. So eta 1, the intrinsic impedance of medium 1, is complex here, because we're talking about general medium. So this half space, let me shade it. So this half space is medium 1, and it extends to infinity. Similarly, that half space is medium 2, and extends to infinity. So we want to know the field at medium 1, the fields at medium 1 and the field at medium 2. So the wave will impinge upon medium 1, upon the interface, then part of the wave will be transmitted, some part of the wave will be reflected back in medium 1. So this one, let me call it impinge. This one reflect. This one transmit. So the reflected wave will be given by the impinge, also like incident. So the reflected wave ER will be reflected back, so it's going to propagate back into the negative z direction, and the magnitude of that will be ERO. So it's going to be the same complex wave number, but it's going to propagate in the other direction. So this one should be along the positive AX. So the reflected magnetic field will be this form, and this one should be the negative AY. Why? Because in this area we have, or for these two fields, we have to satisfy this equation. So AK is positive AZ, AE is positive AX, so AH should be positive AY. Here, this equation so AA is still positive AX, AK now is negative AZ, that means AH should be negative AY. Now the last component is the part of the field that's been transmitted to medium 2. So I can write it in the same form, T naught. Now medium 2 is characterized by gamma 2, not gamma 1. The wave is propagating along the positive z direction, and the direction of propagation, or the electric field, has an x component. The magnetic field is now has y component, and it's been scaled by the intrinsic impedance of medium 2, which again can be complex. Okay, now we wrote all the expressions for the fields. Now we want to find their magnitudes in terms of the incident wave. So of the incident wave, let me add one page here. If the incident wave so remember the point here is write the fields in terms of the incident wave. Or the incident field. So in order to do that, we need to apply the boundary conditions. So we know that in order to apply the boundary condition, the tangential component of the electric field, or first of all, before that, the electric field in medium 1 consists of two parts: the transmitted or the impinging or the incident electric field and the reflected one. The electric field in medium 2 consists of only one part, which is the transmitted field. Same thing applies for the magnetic field. So E1 should be E incident plus E reflected. E2, which is the electric field at medium 2, should be only E reflected, E transmitted. The magnetic field in medium 1 should be also the magnetic field, the incident magnetic field, plus the reflected magnetic field. The magnetic field in medium 2 should be only the only the transmitted magnetic field. Therefore, we need to apply the boundary conditions. So, at the interface between these two medias. So this is the point z equals to 0. So if we take these equations and set z equals to 0, and apply the boundary condition, we will see that so at z equals to, let me go back to the blue one, at z equals to 0 we have E1 tangential should be equal to E2 tangential. This is from the boundary conditions that we studied. H1 tangential should be equal to H2 tangential. Notice here that all the electric fields, so the normal component should be along the positive, should be along the z direction. However, all of the expression, all of the electric fields that we have are along the positive, along the x direction. Similarly, all the magnetic fields that we have, they are along the y direction. That means all of these fields, all of the fields that we have are along the our tangential components. So there is no need for decomposing the field in medium 1 into tangential plus normal components, and there is no need to decompose the field in medium 2 into tangential and plus a normal component. So we can apply these two conditions directly into the field expressions. So if we apply that, we have E incident 0 plus E reflected 0 equals to E transmitted 0. So in this case, E incident 0 here, if we substitute z equals to 0 here, we'll get E incident naught. Similarly, if we substitute z equals to 0 here, and the reflected part, we'll get E reflected naught. And finally, if we substitute z equals to 0 and the transmitted part, we'll get E t naught. So this one simplifies to plus equals to E tangential naught. Similarly, if we apply the second boundary, this is the first one, this is the second one, we're going to get something similar. However, we have a factor of eta that we should keep in mind. So all of the magnetic fields in medium 1 are expressed in terms of eta 1 minus again. Here we did not do anything fancy, so all what we did was substitute z equals to 0 in the magnetic field expressions here, here, and finally there. Therefore, we can manipulate these two equations, and if we do so, we will end up with, we want to write A reflected naught in terms of A incident, and we want to also write A transmitted naught in terms of A incidence. So A reflected naught in terms of A incident is eta 2 minus eta 1 divided by eta 2 plus eta 1, and this one here. A transmitted naught is 2 eta 2 divided by eta 1 plus eta 2 times A incident naught. So this term is defined as the reflection coefficient gamma this term is known as the transmission coefficient tau. These two equations are very important, so let me put them in a box here. So gamma is E reflected divided by E incident. Tau is E transmitted divided by E incident. So these two equations are very common. We'll see them soon, inshallah, when we talk about transmission lines. However, the intrinsic impedances here are replaced with the characteristic impedance of transmission lines. So the notion of dividing the electric field into two components, or expressing the magnetic field or the reflected field in terms of the incident field using the reflection coefficient, is very common in all of the electromagnetic problems. So in this case, we can actually write E1 as I'm missing gamma here. This one, gamma 1. Similarly, I can write E2 as tau so once I know this value and I know the intrinsic impedance of these two media, I can determine the electric field anywhere. So there are some properties of this reflection these reflection and transmission coefficients. So the first one is 1 plus gamma should be equal to tau. This comes from the boundary condition. So at z equals to 0, we have 1 plus gamma equals to the electric field at medium 2, which is tau. The second one is, well, those are reflection coefficients, so they are dimensionless. And third one is gamma ranges between 0, the magnitude of gamma ranges between 0 and 1, and gamma can be complex. In fact, whenever we have complex intrinsic impedance, then gamma will be complex. So the fact that gamma ranges between 0 and 1 is to satisfy the law of conservation of energy. So in the following lecture, the following part, we're going to talk about special cases when the wave propagates between two special media. For example, one of them is lossless dielectric, the other one is perfect conductor, or free space and lossless dielectric. But before that, let's take an example and to make sure that we understand the concept here. So we're given here in a free space. So whenever we see the word free space, it means epsilon relative is 1, mu relative is 1, and the wave velocity is c, which is the speed of light. We have a plane wave. We are given the magnetic field, and we are given that it's incident normally on a lossless medium. So medium 1 is free space. This one is free space. Or I can write mu naught epsilon naught the other one is lossless dielectric with 2 epsilon naught 8 mu naught, and this one for z greater than 0, this one for z less than 0. And we want to find the reflected fields as well as the transmitted field. So the very first step is actually determine the first step is actually to determine what is beta here. And so beta is not given. We are given the direction of propagation to be the positive z direction, and we want to find beta, and we want to find eta 1 and eta 2. So eta 1 is eta naught, since it's free space, which is 120 pi ohms, or 377 ohms. Beta 1 is omega divided by c, and we have omega 10 to the power 8. C is 3 times 10 to the power 8, so beta is 1/3 radian per meter. And for eta 2, so beta 2 should be omega mu naught mu epsilon. So we know omega, and we can write the square root of mu epsilon as mu naught epsilon naught mu relative epsilon relative, or divided by c. So mu relative times epsilon relative is 16, the square root of 16 is 4, so it's going to be 4 times beta 1. And we found this one when we talked about beta in medium 1. So 4 divided by 3 radians per meter. Now, so to find the incident field in medium 1, we multiply the magnitude of the magnetic field by the intrinsic impedance. So that's going to be 10 times 120 pi. The magnetic field is along the positive AX direction. So AX AZ, which means this one has to be negative AY. Therefore, A incident should be negative 10 times 120 pi, which is 2000 pi cosine, we know omega 10 to the power 8 t minus beta 1, which is 1/3. This one should be along the negative AY. A reflected should be gamma times the magnitude of A reflected should be gamma times the magnitude of A incident. Gamma is eta 2 minus eta 1 divided by eta 2 plus eta 1, and we forgot to solve for eta 2, so let me go back and solve for eta 2. So eta 2, since it's a lossless dielectric, so it's going to be always of the following form, and it's going to be 2 times eta naught, or 240 pi. So the reflection coefficient here would be 2 eta naught minus eta naught divided by 2 eta naught plus eta naught, which is 1/3. So 1/3 of the field, which means 1 to the power 9, 1/9 of the power is reflected. Which means, in this case, the A reflected should be along 10 times eta naught divided by 3, which is 1200 pi divided by 3, 400 pi cosine 10 to the power t. Since this part is reflected back, so the direction of propagation will be the opposite to the direction of propagation of the incident field. So it's going to be in the positive z direction. This has to be along AY. Now, the reflected magnetic field will be the reflected electric field divided by eta naught, which is going to be negative actually. For 100 divided by 120 pi cosine 10 to the power 8t plus z divided by 3 x. And if I simplify this one, it's going to be negative 10 divided by 3 cosine 10 to the power 8t plus z divided by 3 x. Now we found the reflected field. The last part that we are asked about is to find the transmitted field. So remember, the magnitude of the transmitted field, transmitted electric field, is going to be, or the transmitted electric field is going to be tau times the incident electric field. So in order to find tau, we can either use this equation, 2 eta 2 divided by eta 2 plus eta 1, or use this equation. So both will give us tau equals to 4 divided by 3. That means the transmitted electric field will be the incident electric field, which is here minus 1200 pi multiplied by tau, which means minus 1600 pi cosine 10 to the power 8t. So the frequency will stay the same, the frequency will not change, and we should change the phase constant to match the phase constant in medium 2, which we found to be 4 divided by 3. So this one along the negative AY. The transmitted magnetic field will be the transmitted electric field divided by the intrinsic impedance, which was 240. And if we simplify the magnetic field, we will get 20 divided by 3.